In this lesson, I want to go through some actual nuclear decay equations using the symbols that we had in a previous lesson. And before I get started, just let me say, in the boxes you'll see examples of each decay type. And what I've done was try to be pretty accurate as far as the particles that were emitted. I didn't really include the gamma radiation that occurs with each of these. So this is just a particle kind of a reaction, not an energy balance. We're not going to worry in pre-AP chemistry in 10th grade about the antineutrinos like you see circled here, or the neutrinos that are in other types of reactions. If you're interested in these particles and some more of the nuts and bolts about what goes on inside the neutrons and inside the protons as quarks are rearranging and changing their quantum states, I want to refer you to the UIL science book we used last year called Higgs. It's a summary of the Higgs boson discovery process by Jim Baggett. I have a couple of copies on my bookshelf at school, and if you're interested in this type of stuff, then you might want to give that a read. But anyway, for us, let's start with an alpha decay here. In an alpha decay, remember this is when the nucleus is just too big. It's impossible to stay together from all the proton-proton positive repulsions. Not enough glue in the world to hold it together. So let's start with the first example that you have on the right-hand side. It is Lawrencium 256. And of course the atomic number is 103. Well, this is a pretty big element. So anything with an atomic number greater than 83 has a very high probability of undergoing alpha decay just because of its size. So we know that this will be an alpha decay. And then to figure out the rest of our nuclear equation, it's just a mass balance and it's a charge balance. Conservation of mass, conservation of energy. The top line, if we could say 256 equals 4 plus something. Well, that's 252. So the top numbers have to add up to equal 256. Likewise, the bottom numbers, so whatever I put here, needs to add up to equal 103. So 2 plus what equals 103, and that's going to be 101. The last piece of the puzzle then, what is the symbol for this element? We go into our periodic table. Element 101 is Mendelevium. And I get that from the periodic table, atomic number 101. So that is an alpha decay equation. Going to the bottom for beta decay. In beta decay, you're going to have an atom that has too many neutrons. So a neutron is going to become a proton. So if we start with our example and following the model here, helium-6 isotope is going to beta decay. It's going to have, before I do it, let's just think about it. It's got 2 protons and it's got 4 neutrons. That ratio is 2 to 1. It's supposed to be 1 to 1. So it has twice as many neutrons as it is supposed to have. So it is going to beta decay and try to fix that. So we'll put the symbol for a beta particle. I prefer the electron one, the 0, -1e. You can definitely use the beta if you prefer it. And then I'm going to do the same thing I did for alpha. The top numbers have to add up or form an equality. So 6 equals 0 plus what? And that's going to be 6. And then we do the same equality with the bottom numbers. 2 equals -1 plus what? So be careful with that. 2 equals -1 plus, I need a bigger number there, so it's actually going to be 3. You can say that backwards now. 3 minus 1 equals 2. It may make more sense. So to figure the symbol out, let's go back to the periodic table. Element number 3 now is going to be lithium. So the new isotope made here is lithium-6. And just kind of looking at it, the neutrons now are 3, protons are 3. The ratio is 1 to 1, just like it's supposed to be. I actually want to do 2 beta because they're somewhat harder than alpha. I guess I can acknowledge that. So let's do the very next example. We have sodium 24. It has a 13 to 11 ratio. That's going to be slightly greater than 1, so we would see and probably predict a pretty low half-life on this one. Nothing too serious, but it will still beta decay. And our top numbers, 24 equals 0 plus, so still 24. Mass is conserved. And across the bottom, 11 equals -1 plus something. That's going to be 12. So we increase the atomic number in beta decay, and that will make magnesium. Alright, now we come to the cool ones, the ones that not everyone will learn. Positron decay, we talked about before, occurs when you have not enough neutrons, so the nucleus is going to try to rectify that by converting neutrons into protons into neutrons. So in this case, we will make the positron. I showed you that symbol before, and this time we will get a neutrino that we are not going to worry about for our class. So doing some examples, we start here with bromine 75. Kind of a weird one here for positron, so I'm not even sure this one's real, so I'm going to avoid telling you why on this one because I'm not sure it's even legitimate. But we're going to work it and pretend like it is. So we're going to make a positron, so 0 plus 1 E. Remember, it's the opposite, it's the antiparticle of an electron. And we do the same mass and energy balance, mass and charge balance. 75 equals 0 plus, so still 75 on top. Wow, I promise. And then across the bottom, 35 equals 1 plus. So this one is going to have the opposite effect of beta decay, and it's going to cause the atomic number to go down by 1. From the periodic table, atomic number 34 is selenium. One more example of positron. If we take phosphorus 30, and phosphorus is a good example of a positron emitter because it is a small atomic number element and the ratio is right at 1. And so it would be, this particular isotope I think is an error. I think it meant 29 over 15. But the ratio about 1 to 1 is right on the border, so it could go positron and try to make one more neutron to add glue to the nucleus. At any rate, we'll do a positron, and the other particle will be 30 equals 0 plus, so no change in mass. And then across the bottom, 15 equals 1 plus 14. So we are decreasing the atomic number to make silicon. And then finally, we have electron capture. And if you look at the example in the box, this one is uniquely different from the others because now the particle is on the left-hand side of the reaction and not the right. It is a reactant, not a product. So when we write this, keep in mind the electron is being absorbed into the nucleus where it is merging with the proton to generate a neutron. That's the mechanism. In our first example, this is argon 38. Argon 38, see, I already messed up. That should be a plus sign. This is going to be electron capture, so we put the capture in, and then the yield sign. Now, keeping it across the top consistent, 38 plus 0 equals, so that stays the same. And then across the bottom, 18 plus -1 equals 17. Again, it's the same, not the same mechanism, but the same effect as positron decay. Atomic number 17 is chlorine. All right, let's see if I can do another example and not screw it up. So we have strontium 80. Strontium 80 is going to undergo electron capture. So the electron's on the left-hand side. 80 plus 0 equals 80. 38 plus negative 1 equals 37. And from the periodic table, element number 37 is rubidium. All right, now I want you to try the rest of the examples for each type, and we'll check them tomorrow in class.